All right, so continuing. These examples are great, and I think if you understand them, if we're looking at a differential equation with constant coefficients, and if the polynomial, the p of d, if it just factors into linear factors, then that should be it, right? I mean we can solve any of them, right? But there's more than that. In fact, we already seen in the first example, one of the first examples I did in day one, y prime prime plus y equal to 0, which is important. That's like simple harmonic motion, right? Spring without friction, if you like. That had solutions which were sine and cosine. Where are those? Those aren't here, right? I mean, we've got exponentials, x squared times exponentials. The constant function 1 is over here, right? Here, one more example. This sometimes gets you guys. What if I had y prime 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 equal to 0? I mean, we don't need the machine, the beast that we just built to do this one, do we? So this, we get d cubed, y equals to 0. So it's really d minus 0 cubed. I mean, however you want to look at it. Anyway, it's lambda equal to 0 thrice. So our solutions are 1, x, and x squared. And the general solution is this. Now I think this was a fair question before you darkened the doorstep of this course. I mean, you just integrate 3 times. That's the solution, right? Integrate 1 time, you get y prime prime equals to a constant. Integrate 2 times, you get that constant times x plus another constant is equal to y prime. Integrate a 3rd time, you get y is equal to what we wrote. So you just integrate 3 times, and that gives it to you. But of course, we can also see it from our lemma here. Okay. So what about complex factors? How does that play out? How do we deal with complex factors? That's what I want to talk about now. So I need to just hit pause on the differential equation solving for a second and just talk about how do you deal with complex valued functions. All right. So let me give you an example. Again, not following example 11, but how to differentiate functions that go from R to C. So if a function, so this is a complex valued function of a real variable, something like this. Z equals to, say, sine of t plus I times e to the t. Here, I squared is minus 1. So what we're looking at is a formula for a complex valued function of a real variable. How do we differentiate this? What does dz dt look like? All right, so what you do, it's really simple. You differentiate the real part, and you differentiate the imaginary part, and that's it. You just differentiate component-wise. All right, and that's it. That's how to differentiate a complex valued function of a real variable. Game over, end of story. So the definition, if we differentiate with respect to time, or I guess I could say x. We've been using x a lot today. So d dx of u plus iv. Here u and v are, I'm thinking of them as being real functions. All right, so u is the real part and v is the imaginary part of this complex valued function. Well, the way you do this derivative is it's really simple. It's just du dx plus I times dv dx. It's just the most natural thing. That's how we differentiate a complex valued function of a real variable. Now here's the beautiful thing. So there's something called the complex exponential. And here's the way it works. If we have e to the alpha plus I beta times x, all right, that is equal to e to the alpha x times the cosine of beta x plus I times the sine of beta x. Now, maybe you've already seen part of this in like calculus 2. Most professors at some point will show you that e to the I theta is cosine theta plus I sine theta. I'm pretty sure Dan Joseph does that. I'm pretty sure Dr. Skambordis does. Odds are pretty good that you've seen this. I know I do. Anybody ever has anyone not seen this before? You? Okay, so this, what I just wrote, is called Euler's identity. What it does is it relates sine and cosine to the so-called imaginary exponential. All right. But that's how we define the complex exponential. There it is. I mean, it's a combination of real exponentials and sines and cosines. And fun fact, the derivative with respect to x of e to the lambda x is equal to lambda e to the lambda x even for lambda equal to alpha plus I beta, with beta not equal to 0. The chain rule still works out. And if you study the calculus we did before the break, it's all still valid when lambda is complex. That's pretty cool. So what that says is if I have a complex factor in the polynomial, I can get a complex solution. All right. A little bit more theory I need to tell you. Nothing too big, really. We'll see this again and again in the course, though. So we've got some kind of like algebraic machine we're using to solve the differential equation. It comes to some polynomial somehow. The polynomial allows for either real factors or complex factors. For the complex factors, typically, what we're going to see is we get some kind of complex solution to our differential equation. All right? It turns out that that single complex solution is going to have two real solutions in it, and they're going to be linearly independent. So every complex solution is going to give us two real solutions. And it also so conspires so that like the complex, since we're dealing with real polynomials, the complex conjugate is always coming as a pair. So let me show you an example before I be too out in the clouds here for you. How about this? So y prime prime plus y equals to 0. We have d squared plus 1 acting on y equals to 0. So I don't know if you knew this or not, but you could factor that as d plus I times d minus I. See, because 1 is equal to minus I squared. So this is really the difference of perfect squares from a complex perspective. All right, d plus I, d minus I. So, you know, this would give me lambda equals to minus I. This would give me lambda equals to I. Given our fun fact, all of our lemmas still go through, and we find complex solutions. Complex solutions, e to the minus ix and e to the ix. All right. And it is true that the general complex solution would be c1 e to the minus ix plus c2 e to the ix. I'm not even going to write that down, though, because that's not what we're after. We're after real solutions to real differential equations in here, right? So we need to figure out how to extract from this the real solutions. The answer is an Euler's identity for this one. See, because e to the ix is cosine x plus I sine x. So the real part of e to the ix is cosine x. The imaginary part of e to the ix is sine x. These are real functions. All right? If we used e to the minus ix, what would the difference be? It would give us minus sign instead of sine there. But you know, as we derived yesterday, general solution is what? c1 cosine x plus c2 sine x, right? So the cosine and the sine, these are appearing as the real and imaginary parts of a complex solution. There are two complex solutions. They're a conjugate pair, plus or minus I, right? We only need to use 1/2 of the pair to get everything we need. So the theorem I was about to write is this. If L of Z equals to 0 is complex solution to, real ODE L of Y equals to 0, then Y equals to the real part of Z and Y equals to the imaginary part of Z are both solutions to star. This is not, the proof is really just that since Z is equal to the real part of Z plus I times the imaginary part of Z, I mean, that's how we define the real and imaginary part. And since L is a linear operator, it pretty much follows from that directly. Let me not prove it because I think our time is better spent with examples than the time that remains. But this is the start of the proof. All right, so what example am I on? 14? Yeah. Y prime prime plus 4y prime plus, let's see here, 5y equals to 0. So this would be d squared plus 4d plus 5 acting on y equal to 0. Can this factor? No, not over the reals. It's an irreducible quadratic. And you can see that from completing the square. This is d plus 2 squared plus 1. If you complete the square and you get a plus, that means it's irreducible. And once you do that, you can read from this what the alpha and beta are. So this tells me, by inspection, that alpha equals to minus 2. Is that right? Yes, minus 2, and beta equals to 1. You could go minus 1, but I'll do 1. And the lemma I haven't written down, but I probably should. If we have d minus alpha squared plus beta squared acting on y equals to 0, this has y1 equal e to the alpha x cosine beta x, and y2 equal to e to the alpha x sine beta x as solutions. Let me show you why that is. So, I guess I'm out of time, though. Here then. Oh, no, I have 5 minutes. Let me chill. Okay, so, let me, for the sake of pedagogy, let me show you. I mean, you don't need to do this to solve it. Like, fine. Let me just write down the solution. That's what I expect you to do, honestly. So once I see this, I can write down next step, general solution, y equals to c1 e to the minus 2x cosine x plus c2 e to the minus 2x sine x. Great. Game over. That's it. All right. Now, what am I doing there? What's the internal logic of that? Let me explain that now. The internal logic of that is this complex solution business. So this is really d plus 2 minus I times d plus 2 plus I. So in other words, I've got lambda equals to minus 2 plus I, or lambda conjugate, which is minus 2 minus I. Focus on this one. E to the lambda x is equal to e to the minus 2x times e to the ix, which is e to the minus 2x cosine x plus I e to the minus 2x sine x. That's a complex solution to the differential equation. The real and imaginary parts of that give me what I wrote next to C1 and C2. All right? So we go up to the complex number system to find solutions, right? But we don't stay there. We use those to extract the sine and cosine solutions like I just did. Does that make sense? Perhaps I should do another example? Most likely, right? Let's see here. How about if we have d squared plus 4d plus 3 times d squared plus 1 squared. Now, you guys know that this right here, what happens if we complete the square on that? Complete the square on this, what does it give you? It gives you d plus 2 quantity squared minus 1. Aha! Not irreducible, right? In fact, that's really what? That's d plus 1 times d plus 3, right? In fact, the first term does factor. Completing the square is general, right? You complete the square. When you complete the square, if you end up with something squared minus something, that means it could be factored over the reals. If you end up with something squared plus something, that means it can't be factored over the reals, right? That's the difference. Now, I made our life easy. This is just d squared plus 1 squared, because we're almost out of time. Okay, so let me just sort of quickly run through the logic here for you and write down the answer. So this term right here tells me I get an e to the minus x as one of my fundamental solutions. This says I get an e to the minus 3x as one of my fundamental solutions. This says that I get complex solutions, e to the ix, e to the ix and x e to the ix as complex solutions, right? But every complex solution has within it two real solutions. So the e to the ix actually gives me cosine x and sine x, and this one actually gives me x cosine x and x sine x. What I wrote in blue, the linear combination of those, is the honest-to-goodness general solution to this sixth-order differential equation. All right, so here we go. Y equals to c1 e to the minus x plus c2 e to the minus 3x plus c3 cosine x plus c4 sine x plus c5 x cosine x plus c6 x sine x. Hopefully this answers one of your questions that I think you guys would probably have asked me if I gave you a chance to ask it. Like, what happens when there's a repeated complex root? Like we've seen for repeated real roots, we get x e to the x, x e to lambda x, x squared e to lambda x, and all that. Repeated complex roots give you things like x times cosine or x times sine, or possibly also times an exponential. And that's it. That is how to solve any constant coefficient nth order differential equation, because you can always factor a polynomial into real factors or irreducible quadratic factors, and that's all that's out there. This is algebra, right? So tomorrow we will see how to find particular solutions do not be discouraged in the quiz. Do your best. If you don't get some problem, it's not the end of the world. Just do your best. Try to do it. I have one problem which has like 4 of these. I've tried to include every case, like distinct real, repeated real, and quadratic, and then there's like a third order one. But you should be able to do that one. I made it worth 8 points. Your quiz is worth 50 points. It's like 15 problems or so. Some of them are from the recommended homework. Some I actually tell you where they're from. Some I just didn't tell you where they're from. But I hope you can get them. You can email me if you get stuck on stuff. I will try to check my email later. But it is due tomorrow at start of class. Such is life in here. Sorry about that.
Is it posted already?
It is posted in course content. Enjoy.